So don't like neglect this opportunity. We really want to work with you. That's on my side. Also, same for, can give feedback for TAs, feedback for instructors, anything. We are all reading this allocation and all the instructors, and it's anonymous. That's it.
Yeah, you can also say something like this: don't get this slide, please repeat it, or anything that just comes to your mind. And office hours. I think all of us are very lonely.
Only during that 1 hour, though. Aside from that, we're okay.
So if you are lonely too and you are looking for
You have to be careful what you say. We're recording this. All right, thank you. That was good. So any questions about anything? So today we're going to finish the KKT conditions, and then we're going to move on to our last lecture in terms of duality and stuff for this section. We'll return to duality again later when we talk about algorithms. We'll talk about some dual algorithms. So this is what you learned last time, the KKT conditions. I claimed, and I still would argue, that these are one of the more useful things you can learn in this course. So make sure that you remember them, that you understand their role in characterizing optimality. And, if you can come up with some clever acronym to remember stationarity, complementarity, slackness, primal and dual feasibility, then please let me know, because I'm not aware of any. But yeah, so these are the 4 conditions. So they basically say that if we have this problem, it's a constrained optimization problem, and the variable is x, that I am going to add a dual variable for every one of my inequality constraints and another variable for every one of my equality constraints, u and v. And these are conditions on x and u and v. So the first one says that the point x has to minimize the Lagrangian evaluated at uv. So it has to it has to achieve the minimum of f of x plus the sum of ui hi plus the sum of vj lj. The second one says that the product of ui with hi of x has to be 0. It's called complementary slackness. So it means that either one of those constraints, that ui is less than or equal to 0 or hi of x is bigger than or equal to 0, at least one has to be tight, has to be at the boundary. And the last two are just that the points x and uv are feasible for their problems. So that x satisfies all these constraints, and that u is, I'm sorry, I said negative, but u is bigger than or equal to 0 in each component. Okay, so what we learned last time was that these conditions are always sufficient for optimality. So if I satisfy these conditions, then I have found, if I find an x and a uv pair that satisfy these 4 conditions, then that implies that x is primal optimal and u and v are dual optimal. That's a very powerful statement. And we also learned that the converse is true under strong duality. So if we're in a situation where we have strong duality, where the primal and the dual objectives are equal at the optimum, then these are also necessary for optimality. Okay, so the canonical problem we think of as a convex optimization problem, where we have a point that strictly satisfies the inequality constraints. If there exists a strictly feasible x, that's called Slater's condition, and we know that strong duality holds. So in that canonical problem form, the KKT conditions are necessary and sufficient for optimality. So they completely characterize optimality. Are there any questions about them? Okay, so let's just jump right ahead to the examples. I didn't cover this example last time because we didn't get to it. And we'll go through this example of the lasso problem and also of the group lasso problem and see what the KKT conditions say for us in those 2 problems. Okay, so we've seen this a number of times already. It's the sparse regression setup. So I want to find beta to minimize this objective. So what are the KKT conditions here? Well, this is an example where I said last time, there are no constraints. So what does the KKT conditions mean? It means just taking a subgradient of this objective and saying that 0 must be a subgradient. Because when there's no constraints, right, the stationarity condition just reduces to 0 being a subgradient of the objective function. We already knew that characterized optimality. Right? That was from our subgradient lecture. But we tend to still call it the KKT condition sometimes, just because this is the most general formulation of a characterization for optimality. So what does it mean that we have an optimal point here? Well, let's just take a subgradient of this criterion and set it equal to 0. So we can decompose it into a subgradient of this plus a subgradient of that. So we want 0 to be in the subgradient of the first term. It's differentiable, right? And so what's its gradient? X transpose y minus x beta, right? So hopefully people are just shy because we started the class and that one is natural to everybody. Like the QP, or like the explicit minimizer of a quadratic, this should be second nature to you. You should just be remembering this because we'll see least squares lost a lot. It also, you should just think of the chain rule here, right? I'm just taking the gradient of a function and I'm just applying the chain rule to get this x transpose out in front. And the subgradients of the second part, again, we've seen that a bunch of times. They look like lambda, I guess we'll call it S here. Is that what I call it on the slide? S. So I'll say that 0 has to be equal to x transpose times y minus x beta. Wait, so there is a negative sign here, right? That's not the gradient unless I put a negative sign or flip the order here. Where S has the property that it's equal to the sine of beta I if beta I is not equal to 0. And otherwise, it's just between minus 1 and 1. So a vector beta is optimal for this problem if it satisfies this for some subgradient S of the L1 norm evaluated at beta. So let's just rearrange that. That tells us that xi, we'll look at it in each component. Xi transpose y minus x beta is equal to lambda times Si. I just looked at the ith component of each side and I moved this to the other side. Okay, so this already tells us a few interesting things about the lasso solution. What's the first thing it tells us? Well, what happens if I look at a variable for which xi transpose y minus x beta is less than lambda in absolute value? What do I know about that variable? Or what do I know about that component of beta at the solution? What's that? Yeah, I claim that this implies beta I equals 0 at the solution. Why is that the case? Yeah, right. If beta I was not 0, then look, this is a characterization of the solution here. This tells us the exact property of the solution that if beta I is not 0, then Si is equal to plus or minus 1. So we have to have xi transpose y minus x beta equal to either lambda or minus lambda. It can't ever be strictly less than lambda. It can only be strictly less than lambda if we took the subgradient to be strictly between minus 1 and 1. That's only a subgradient when the ith component of beta is 0. Okay, so this tells us something like if the correlation, if I think about x as having like unit norm, of the ith variable in the residual, y minus x beta, is less than lambda, that implies that it's not active at the solution. I'm just going to call it 0 at the solution. Right? So this is telling us something about the 0 variables. What happens if I have xi transpose y minus x beta equal to lambda? What does that imply? What's that? Beta is plus 1 or minus 1. No. What's that? So this implies that SI is equal to plus or minus 1. And then you said this implies. Okay, so one of those two things is right, but this last one is not. So it does imply that the subgradient is plus or minus 1. We actually don't know that that implies that beta I is not 0. Right? Because look, the subgradient when beta I is 0 is anything between minus 1 and 1 inclusive. It could have been 0. So just be careful that you're not inferring the wrong kind of information, right? So it's easy to go one direction. The other direction is not really necessarily true. Okay, so this is a fact we just read off from the problem. It's going to help us in a bunch of ways. In fact, on the next homework, on homework 4, you're going to have a problem that uses this to great advantage as a way of screening out variables from the optimization problem before you even solve it. Okay, so there's a way to check whether this is true before we solve the problem. If we know it's true before we solve the problem, we don't have to even include, say, the column of x corresponding to variable I, xi, in our problem, because we know that beta I would be 0 already. Okay, so that was the lasso. Here's just a quick one involving the group lasso. So we haven't seen this problem before. Now the KKT conditions give us a little bit of intuition as to what it's doing. So the group lasso is a problem that people use when they want to do group variable selection as opposed to just individual variable selection. So I think about a problem where I've decomposed my coefficients beta into, say, I guess I call it G groups. So this is a decomposition of my coefficient vector into G blocks. So each one has P superscript I variables. So they're not necessarily the same size. And these groupings come ahead of time. It's like we believe that it's a natural grouping for these variables, say, in the regression problem. So I solved the usual least squares regression problem. But now the penalty that I add is not one that selects individual components of beta, but that selects entire groups of beta. Okay, that I multiply by a weight, Wi, times the ith block of the component vector in L2 norm. Okay, so it may not be obvious why the L2 norm here is going to give us the right behavior in terms of the solution. At least that wasn't obvious to me when this problem was first formulated. Right, so this seems eerily close to the L2 squared norm. And if I had a squared there, then we know that's not going to give us anything that has zeros in it. It's just like doing ridge regression. We could write out the solution explicitly, and it just would be kind of moving the components of beta towards 0. But somehow when I don't have the squared, if I have just the L2 norm, it turns out to do the trick. We select blocks of variables at a time. This is a problem that lots of people studied after its proposal, and it's become kind of quite popular for group variable selection. So we're going to look at the KKT conditions, and they're going to give us some insight as to, or some verification that at least we have this property that some groups are entirely 0 at the solution, other groups are not. Okay, so it's really a very similar calculation to the lasso case. There's no constraint, so all I'm doing is taking a subgradient of my criterion and setting it equal to 0. So the first part is just the same as before. So I have 0 equals minus x transpose y minus x beta. And then I have plus lambda times, now let's suppose I'm going to look at the entire subgradient block for group I. Okay, so I'm going to write down the subgradient. So here I wrote down the subgradients, for each variable, I equals 1 through p for the lasso. And then here I'm going to do the same thing. I'm going to make it for I equals 1 through g. So each one of these is actually going to be a block of variables. So I'm going to have x, I transpose, because it's going to be the variables corresponding to the ith block, which is a little more general than just one variable. And now what's the subgradient of this term with respect to, say, the block corresponding to beta I? Well, I'm going to get 0, right, and everything else in the ith term of the sum, because there's no beta i's in those expressions. And for the ith term of the sum, it's just going to be the subgradient of the L2 norm of beta I times wi. So I don't know what I called that. I guess I called it Si again, where Si is a subgradient of the L2 norm of the ith component block of the coefficient vector. So what is that? Well, we also know what this one is. This is equal to, in other words, this is equal to, it's going to be beta I over its norm when the entire block is not 0. Right, because in that case it's differentiable, it's just the gradient of this. And otherwise it's anything in between, or it's any vector that's in the, I don't know what we'll call it, maybe the ball that has L2 norm less than or equal to 1. When beta I equals 0. Okay, so everybody follow that calculation? So that's I'm just recalling this fact about the subgradient of the L2 norm that we learned back when we talked about subgradients. Okay, so this characterizes the solution. Let's go and write that just a little differently. So I'm going to say that xi transpose y minus x beta equals lambda times wi times this subgradient. Okay, so now we get a similar rule, which is, let's suppose we observe that for the ith block of variables, we look at its L2 norm with the residual, the L2 norm of its inner product with the residual, and we see that it's less than lambda times wi. What does that imply now? If I happen to have I told you I have the solution, I'm not going to tell it to you. All I'm going to tell you is that the inner product of the ith group of variables with the residual and L2 norm is less than lambda times wi. What could you conclude from that fact? What's that? The entire component block. Yeah, all of the components of the ith block are 0. So why is that true?
If they're non-zero, then the L2 norm of Si would be less than, would be equal to 1.
Right, yeah. So if beta I were non-zero, then its subgradients look like this, right? It's beta I over its norm. And that has L2 norm 1. So we'd have that the inner product of xi with the residual is lambda times wi times something with L2 norm 1. So if I were to take the L2 norm on both sides, I would get that the L2 norm of this is equal to lambda times wi times the L2 norm of this guy, but this is 1 when it's non-zero. So it wouldn't be strictly less than lambda wi. It'd be exactly equal to it. So it's only less than lambda times wi when we have this. Okay, so that's another nice property that we can read off. And again, I'm not sure if we'll cover it in the homework, but there are rules that now you can deduce from this that will allow you to exclude groups of variables from the solution ahead of time. So this is also convincing us that we get the property that groups of variables are 0. Right? Because whenever this happens, we get a group of variables that's 0 the solution. we can also go a little bit farther, and we can try to write this in a way that gives us an expression for beta I. Now this is not going to be useful for any particular purpose at this time, but you can see kind of how you might start to use these KKT conditions to derive expressions for the solutions that are kind of implicit. But nonetheless, they are, they do tell you a property of the solution. So let me write this as y minus xi beta I guess minus the sum of all j not equal to I of xj beta j. So I've just expanded out this product x beta as the matrix, multiplication of xi with the ith group of beta and then all the rest. And so just think in all these calculations, like I'm just generalizing the case where each group is one variable, right? If you're getting kind of a bit lost with the block structure, it's really just the same as each group being one variable. I still have this equal to lambda times wi times si. Okay, now I'm going to say, I'll just do this calculation if beta I is not equal to 0. I want to get an expression for it in the case it's not equal to 0. So in that case, I can replace the subgradient with beta I over its norm. Now I'm going to solve this for, I'm going to try to solve this for beta I. So I'll collect all the terms that I have. I have xi transpose xi times beta I. And now I'm going to, I guess I have, sorry, negative of this plus xi transpose y minus all of these things. All this, I'll just call this the I'm going to use a short form. R superscript I means the residual, shall call the entire thing y minus all those guys R superscript I. It'll just be the residual if I don't include the ith variable. So it's y minus the sum of xj beta j for all the rest. I get this equals lambda wi times beta I over its norm. Okay, so now I'm going to cheat, and I'm going to think of this as like something else, something fixed, just so I can get an expression. Again, this is not leading to anything direct. We're just seeing how you might go about learning something about the solution. So I'm going to move this over to the other side, and I get lambda wi over the L2 norm of beta I times the identity matrix plus xi transpose xi, this whole thing times beta I is equal to xi transpose the residual. So I haven't actually cheated it anywhere mathematically, but it's just not going to give me an explicit expression for beta I because I still have beta I here in the denominator. And now let's look at this matrix. Is this matrix, let's suppose wi was positive. Is that matrix invertible, or do we have to know something about x before we determine that this matrix is invertible? Invertible. Why is it invertible?
Transpose x is positive, it's symmetric, and then the first matrix is positive.
Right. So this has, let's say eigenvalues equal to this, right? And those are positive. And this has non-negative eigenvalues. So the whole thing has to have at least a positive smallest eigenvalue. So it's invertible. So I can write now, no matter if x was rank deficient or not, beta I equals xi transpose xi plus lambda wi over beta I in L2 norm inverse xi transpose ri. Okay, so this almost gives us an explicit expression for beta I, but it doesn't really because of this thing right here. But at least it tells us that when beta I is not 0, what are we doing? It's like we're doing regression on all the other variables. Regression on all the other variables would be this. Regression of the residual with respect to all the other variables on that ith group of variables. It would just be like xi transpose xi transpose this response in the regression, which is like the residual of all the other variables, except we add this term, which is a cause for shrinkage. So it makes the coefficients smaller than they would be if we were to regress them, say, just on the residual. So this is still informative, right? It's telling us something about the solution. And it's almost even leading us to an algorithm. I'm not claiming this would converge. We're not going to study this algorithm. But you might try doing something like, I might try cycling through each component block and first checking whether that component block should be 0 by checking this condition. And if that condition is not met, then I'll try to solve it like this, where maybe I plug in for this value here, beta I, and I'll 2-norm whatever it was at the last iteration. So I'll start with a guess at the entire block of coefficients. And I'll go through one block at a time, check whether I should set it to 0. If not, I'll solve it according to this, where I use according to this guy down here, where I use beta I, and I'll 2-norm whatever was in the last iteration, and just keep cycling through. And that'd be a pretty easy algorithm to implement too. Okay, so this is just a flavor of the kind of things you can get from the KKT conditions. You can learn lots of different properties of the solution. Are there questions about this example or the last one? Is that a half question or no question? Okay. So I'm going to skip this last stuff. It's not important for the purposes of the class. There are nice examples that you can go through on your own, or maybe the TA from next week can go through in recitation. These are a little bit more sophisticated things you can say with the KKT conditions, but the arguments are still pretty simple. Just examples of that. Okay, so this result here in particular says that if we look at most L1 penalized optimization problems, where I'm being loose about what I mean by most, but the precise details on the slide, then they have a unique solution, even though this entire criterion may not be strictly convex. Okay, so that's actually somewhat of a surprising fact from the perspective of convex optimization, because usually strict convexity is what we know gives us a unique solution. But in this case, it could be the case that this is not strictly convex, this criterion. But still, by checking the KKT conditions, we can ensure uniqueness of the solution. Okay, let's take a break, and we'll come back and talk about duality. Yes, have a bit of a squeeze here. So this lecture is about the uses of duality. We learned duality, we learned the KKT conditions. We saw some uses for the KKT conditions. Right? Their uses are they basically characterize optimality, so we use them sometimes to solve a problem explicitly, or sometimes to get an idea of the properties of the solution of the problem. Arguably duality is kind of like a larger topic because we use duality to prove the KKT conditions. So one of the uses of duality could be the KKT conditions. But here are kind of two other helpful uses of duality, and there are more. We're not giving an exhaustive list here. The first one, there's not a lot to say about it. We already talked about it, but I want to remind you that if we have a primal feasible point and we have a pair u and v that are dual feasible, so we're able to derive the primal and the dual problems, then if we look at this quantity, f of x minus guv, g being the dual criterion, then this is called the duality gap between x and uv. And we have this helpful relationship, which is that the difference between f of x and f at its optimum, x star, is no more than f of x minus g of v. That's just because this always provides a lower bound, g of v, on the optimal criterion value in the primal for any feasible, dual feasible u and v. So that means that if we're at a point where we have zero duality gap, we have x and uv that have this being 0, it implies primal optimality. It implies that we have x, which is a solution. So it's equal to x star for some solution to x star. And it's the same with the dual points. They're also optimal. So that's one thing that we know from the duality gap. We also tend to use it as a stopping criterion in algorithms. So we haven't talked about primal dual methods yet, but when we do, we'll talk about interior point methods next. Depending on the flavor of interior point method, we often look at the dual, especially if we're looking at what's called primal dual interior point method. And then we use this as a stopping criterion. So it's a very, there's a lot of, a big advantage to using this as a stopping criterion because we actually have a guarantee on how far we are from optimality, as opposed to the other ones we learned before, which are kind of heuristic. Okay, and there are other dual methods that we could use to solve problems we'll talk about in the future, but we all use this as a stopping criterion. We have some guess for the primal solution, some guess for the dual solution. We plug in the duality gap, and if it's smaller than something, say 10 to the minus 5, we know that we're no farther than 10 to the minus 5 in terms of our distance from the primal iterate and its function value to the optimal criterion. Here's another use of duality, and this is the one we're going to be talking about today, and that we could talk about for many lectures, because there are lots of nice examples of this, is that if we have strong duality, so again, convex problem whose constraint set can be strictly satisfied, and we have some dual optimal point, u star, v star, these are dual optimal, then the first condition of the KKT condition, stationarity, it tells us that the prime optimal point, x star, it must minimize Lx u star v star over x. That's just stationarity, right? For x star to be optimal, has to minimize the Lagrangian evaluated at the point u star v star over all x. Oftentimes, this property, minimizing the Lagrangian, can be expressed in closed form. Even if the problem is very difficult, we can express this in closed form. So what it means is that we can actually, from a dual solution, u star v star, get a primal solution, x star. So sometimes the dual is easier to solve than the primal. So maybe we'll write down the dual, we'll solve it, and then we'll just figure out x star from this, the fact that it must minimize the Lagrangian over x. Right? So writing this out just in slightly more detail, this means that we look at when do we have a subgradient, for example, of this being 0. So we just try to solve this expression. This is how we usually write stationarity. Hi of x for x. And if we can, then we get the x from u star v star. Okay, so like I said, this can be a very helpful fact when the dual is easier to solve from the primal. It may look a little bit abstract at this point, so we're going to see some examples that will make it more concrete. So here's an example where it comes in very useful. Let's suppose our problem is the following. This is our primal problem. Want to minimize over all x the sum of fi xi. So this is a, some function of just the ith component of x. So this looks like easy because maybe if this is the whole problem, we could just split this up into, say, if we had n of these, n different minimization problems, right? Because each one of these terms doesn't depend on the other. But I'm going to add this constraint, which complicates things. And it ties all the problems together. And it's a linear constraint that A transpose x equals B. So now these are entangled. We can't really minimize them separately. Okay, so we're going to look at the dual of this problem. And let's assume that each fi is strictly convex. We might even just assume that it's differentiable. None of this is necessary, but it's going to make the example more concrete. So what's the dual of this problem? Well, remember we're going to write down the Lagrangian, L of x, and I'll call the Lagrange multiplier for that v. And that's going to be the sum of fi xi plus v transpose, no transpose. V is just a single, it's univariate, right, because this is just one constraint. B minus A transpose x. Okay, and so the dual function is a function of v alone. So what's the dimension of v? Again, it's just one dimensional. So the dual problem, if we could derive it, is just a univariate minimization problem. So it's going to be a lot easier than the primal. And it's what happens when I take the minimum of the Lagrangian over all points x. That's just how we defined it. So what's that? It's, well, again, the nice thing here is that let me write this as the sum of ai xi. I'll just write that inner product a little more explicitly. If I want to minimize this over x, I can do each one separately. So now actually they're disentangled, just like they were originally. So I'll write it as the sum of the minimum over xi of fi of xi minus ai xi plus vb. So I'm going to go ahead and just call this quantity fi star. Oh, I'm sorry, I missed a v here, right? Should be v times ai times xi. So this is just notation at this point, but actually this means something very concrete that we're going to see in a second. Does anybody guess what this is, this quantity? F star? It's called the conjugate function. Not so important. I don't know why. I thought maybe people might have seen that in another class, or it goes by the Legendre transform sometimes, or the Fenchel dual. But at this point, it's just notation, and we're going to see it in a second. But let's just call that quantity a function of v, because it's a function of v, fi star. Actually, negative fi star of v of ai times v, because I'm going to be treating that as an argument. So then this is equal to right, just the sum of minus fi star of av plus vb. In lots of cases, for lots of f's, we can find these conjugate functions in closed form. So for quadratics, for functions that involve logs and exponentials, usually, lots of different kinds, we can find such functions in closed forms. So depending on what f was, usually I can write down this conjugate, unless it's kind of unusual, somewhat unusual function. So here's my dual problem. It's just a problem in one variable v. Okay, so now let's suppose we were to solve this problem. So we were to solve maximize over all v of g of v, which is definitely an easier problem than the primal because it's just a problem in one variable. And we were to get v star from it. That would be pretty easy, like we said. So how would we get x star from it now? We didn't really care about v star. That wasn't of interest. We cared about the primal solution. Well, we go back to the Lagrangian, and we plug in v star. And we say that x star must minimize L of x v star over x. That comes from stationarity. So what does that mean? Well, we have the calculations all up here. I don't have to rewrite them. They're just up here. So it means that x star has to be the vector whose ith component minimizes this quantity when I plug in v star. So i.e., let's just solve each of these problems individually. That would give me x star, right? It is the point that minimizes the Lagrangian. And it breaks up into different minimization problems, one for each I. And I get that, so how do I minimize this? Well, I assume that f was differentiable, right? So the minimum is given by the gradient being 0, which just is that the gradient of fi of xi equals v times ai. So I solve this for each I. And again, if f is a nice function, this will, this may have an explicit solution. So this will give me just a rule for getting xi star from v star. Any questions about that? Okay, so for example, one of our favorite examples is when, let's say, fi of xi is just yi minus xi squared over 2, like some kind of least squares criterion. Then what do we get for this rule here? How do we get x from xi star from v star? So I'm just translating this expression. What is it? What's the gradient? xi minus yi. And I'm just solving that equals v star times ai. I've already found v star. That was my dual solution. In other words, I have that xi star is just given by taking my dual solution v star, multiplying by this constant ai and adding yi. So I have the primal solution from the dual. Okay, so here's a quick outline of what our goal is going to be to talk about. I'm going to skip dual cones. Dual cones they kind of make sense to talk about in the context of duality, but we'll revisit them when we talk about semi-definite programming and conic programming. So we can just cover that material at that time. There'll be no problem. You won't be asked about it on the homework. So conjugate functions is really the main meat of this lecture. And dual norms, you'll see they have a nice relationship. And then dual tricks and subtleties is just, how do you derive duals? In practice, sometimes you have to do a couple things that maybe look non-standard. So dual norms, we've mentioned these a couple times, so we haven't defined them really. So if we have a norm, some norm, then we define its dual norm as follows. We write it as a subscript star, and we'll call it, its argument y, and it's defined as the maximum value over all points x that have norm less than or equal to 1 of x transpose y. So if this is the norm, this is how we define its dual norm. Okay, so examples of norms are like the LP norms. So like L1 norm, L2 norm, L infinity norm are common ones to look at. We could also look at stuff like matrix norms. We've already introduced the nuclear norm. I used the notation in previous lectures subscript star for the nuclear norm, which is obviously not going to work here. So I'm going to write it subscript nuke. So for any one of these norms, we can define a dual norm like this. Okay, so what do we get from this? One thing to read off from this dual norm definition is that we get a Cauchy-Schwarz-like inequality. I know if I take any two vectors or matrices, whatever these are, if they're matrices, then I think of this inner product in terms of the trace. The absolute value of x transpose y is bounded by, say, the norm of x times the dual norm of y. So this is true for any two vectors x and y, and any two norms, a norm and its dual. So why is this true? It comes right from the definition of the dual norm. We know that y is equal to this. It's the maximum of x transpose y over all points x that have norm less than or equal to 1. So in particular, let me look at the point I'll take the point x over its norm. And I'll call that thing z. So I have the property that z has norm less than or equal to 1. Right? That just comes from the fact that I've scaled x by its norm. So this is true. And I know that y star is the maximum over all points x with norm less than or equal to 1 of x transpose y. So it's certainly bigger than or equal to z transpose y. Right? Because this is just one candidate, and it's the maximum. So it's certainly going to be bigger than or equal to one candidate. Z has norm 1. And what's that? That's x transpose y over the norm of x. Right? So I just move this to the other side, and I get that x transpose y is less than or equal to x times y. And I can do the same thing in reverse to see that minus x transpose y is bigger than or equal to those two quantities, just by taking z to be negative x over its norm. Okay, so I get this inequality. So this provides us with a bunch of really non-trivial inequalities. When we look at the LP norms, this inequality is sometimes referred to as the Holder inequality. But it's more general than that. It just applies to any norm and its dual. Okay, so just duals to remember. We're not going to make you prove them. At least I don't think we are. We may on a mastery set at one point. But duals to remember, here are some duals that are common to remember. The dual of the LP norm is the LQ norm, where 1 over p plus 1 over q equals 1. So that means the dual of the L2 norm is the L2 norm, because 1/2 plus 1/2 is 1. The dual of the L1 norm is the L infinity norm, because 1 over 1 plus 1 over infinity is 1. So this is a relationship for any p and q. And another dual to remember is that the dual of the nuclear norm, this is one that you used on a previous homework, is the operator norm. So the dual of the norm that evaluates the sum of the singular values of a matrix is the norm that just takes the largest one. So again, just helpful facts to remember. And this last one is useful in more ways than it may seem, but it's actually a very useful fact, that if I take the dual of the dual norm, I get back the primal, or just the original norm. And this one, I think we are going to have you prove on the mastery set. Okay, so if I ask for, let's go in this situation, what's the dual of the operator norm then? Nuclear norm. And what's the dual of the LQ norm? It's the LP norm, right? I just take duals on both sides, and the dual of the dual just gives me back the original norm. Okay, on to conjugate functions. Yes?
The definition of the dual norm, how can you use that for matrices?
So for matrices, if I have a matrix A, I think about stringing it out into a vector, and then I apply all of my kind of rules for vectors to that matrix. So if I can string it out into
Y product and sum everything up.
yeah. So the actual definition is like what I said. I just do a consistent way of stringing it out, like column major order or something. But a more concise way of writing the inner product between two matrices, if I treat them as such, is the trace of A transpose B, which is just what you said. You can verify that this matches what you said, element-wise product, and sum them up. Okay, conjugate functions. This is going to be a very useful thing to know for deriving duals. It's going to be like a dual helper. So I have a function f. I'm going to define its conjugate. And its conjugate is going to be another function, which is defined as the maximum over all points x. F is a function of y here, of x transpose y minus f of x. Okay, so the nice picture here from your textbook, the maximum discrepancy between the linear function y transpose x and our function over all possible points x. Okay, so in this example, I ask for the conjugate function at a point y, right? So then I look at this linear function, x transpose y, so it's just x times y because I'm in one dimension. So the line has slope y. I look at f of x, and I look at the biggest I can make x, y minus f of x. And that occurs right here in this picture. So the conjugate function is just defined in terms of that gap. The conjugate function at y is that gap. The biggest I can make x, y minus f of x. And you might have learned it in physics. In physics, they call it the Legendre transform usually, and it's usually treated for differentiable f. Okay, it goes by other names too. So we get a bunch of properties from conjugates, and I guess I almost skipped over one of the most important ones. It's going to be reminiscent of what we learned for duals. One property is that f star is always a convex function. So this is true even if f was not convex. Even f is not convex. So this should remind you of the fact that the dual function is always a concave function, even if the original optimization problem was not a convex optimization problem. Why is this a true fact? If I just look at this, the way it's defined here. Right. For each x, it's a linear function of y. Right? It's just x transpose y minus a constant. And I'm taking the maximum over all such x. So the maximum of a bunch of convex functions, linear is obviously convex, is a convex function in the end result. Okay, so it's a very kind of trivial point when you look at it that way, but it has a big implication. F star is always a convex function. So here are a bunch of properties of the conjugate function. I guess we'll work through a few of them, but some of them I'll leave for you to figure out either on your own or on the mastery set. I don't know which ones we'll put on. But we get this thing called Fenchell's inequality, which is that it's again, it reminds you of the dual norm inequality we saw. A lot of these things, they appear in very similar forms. But for any x and any y, I have the property that f of x plus f star of y is bigger than or equal to x transpose y. So where does that come from? It just comes from the definition, right? This is equal to the maximum over all x. If I stick in just one point x, certainly this is bigger than or equal to x transpose y minus that f of x, and I add that to the other side. And I just get that this is true. Okay, again, trivial to prove, but can be a very useful inequality for various contexts. These ones I'm not going to prove, but you can at least check the first one. I always have that f star star is less than or equal to f point-wise. So if I take the conjugate of the conjugate, it's always less than or equal to the original function. And then this is the most important one, which is that if I take the conjugate of the conjugate, I get back my original function as long as this function is closed and convex. So we didn't learn what closed was. Just think of it as continuous. So the continuous convex function, I have f star star equals f. Okay. The last fact here is that if I have a conjugate which decomposes as the sum of 2 blocks of coordinates, if I take the conjugate of that function, it's like taking the sum of their conjugates. So this helps you in case you have a function that adds up in terms of functions of coordinates or functions of blocks of coordinates. And the fact before that is going to be a very useful fact when we talk about dual decomposition. And so at that point we'll come back to that and we'll inspect this carefully. But at this point it's not important. Yeah?
So isn't the conjugate just the dual of minimizing f with subject to y transpose x being bigger than or equal to 0?
It's a prescient question. The answer is yes. I didn't really listen to the details of what you said, but yeah, it is the dual of an optimization problem involving f, and that's why we like to think of it in this context. So we'll talk about that next, in the next slide or something like that. It's a good insight.
Can you repeat what you said?
It's just the dual of, if you write mean of fx subject to y transpose x bigger than or equal to 0, write the dual problem, just going to be that stuff.
We'll see it in like literally 2 slides. But yeah, good. That's a good insight. So just before we go to that, we're going to look at a few examples. So we can derive conjugates, I claimed, in a bunch of different situations. There are lots of examples in the Boyd and Vannegar book. Here are a few, and you'll do a few on your homework. But if I have a quadratic function, f of x, which is 1/2 x transpose qx, and let's assume that q is positive definite. This is a convex function. I'm going to define its conjugate, right? Just via the usual route. It's the max over all x of x transpose y minus 1/2 x transpose qx. Okay, so here's this infamous form again. What's the maximizer here? The maximizing value x. Everyone's so quiet. It's okay to make a mistake, but most people should get it right. If we all say it together, probably most people will have it right. What's the maximizing value here? Minus q inverse y. No minus. Okay, good. So I plug this in, and I get that the maximum value is y transpose q inverse y minus 1/2 y transpose q inverse q inverse y. So I'm also going to assume it's symmetric. I guess I should have written that down. So it's just equal to 1/2 y transpose q inverse y. So if f is my function, it's a quadratic form in q. Its conjugate is a quadratic form in q inverse. So it's also a quadratic. So what about that first inequality that was really easy to prove? It was called Fenchur's inequality. It told us that f of x plus f star of y is bigger than or equal to x transpose y. Now here that tells us that 1/2 x transpose qx plus 1/2 y transpose q inverse y is bigger than or equal to x transpose y. That's a fairly non-trivial fact. For any x, for any y, and for any matrix Q, this is true. The proof now, since we know conjugate's like 2 lines, but it's non-trivial. That's the case. How about indicator functions? If I have just fx being equal to the indicator that x is in the point C, right? So it's infinity or 0 if x is in C or not in C. Then its conjugate, it's just the max over all x transpose y minus the indicator function of x. Right, so this is going to be 0 when x is in C, and it's going to be infinity when it's not. So that's going to make this whole thing minus infinity. So it can't achieve the max, obviously. So it's just the same as saying it's the max over all x in C of x transpose y. So this we often call the support function of the set C. Okay. I'll come back in just a second. Here's our last example of conjugates. If f of x is a norm, right, LP, nuclear norm, whatever, then its conjugate function as a function of y, it's the indicator that y is in the ball with dual norm less than or equal to 1. So it's 0 when y has dual norm less than or equal to 1, and otherwise it's infinite. So the slide gives a proof of that, that's direct proof. There's a much easier way to prove this, giving this, and the fact that the conjugate of the conjugate is the original function. So let's see if we can see it. Forget about the proof on the slide. That's a backup, because it's direct, in case you forget this fast explanation. So we know that f star star is equal to f for closed convex functions. Okay, the indicator function is closed and convex. I'll just claim that, and hopefully you'll believe me. Because I said that we can think of continuous, but it's convex, and it does satisfy a property called closedness. So it does fall into the situation. So what does that tell us? We know that the dual of the indicator function is the support function. So what's the dual of the support function? It's the indicator, right? So I know that if I ask for the dual of this guy as a function of y, it's just the indicator that my point is in, the conjugate of this function is gives me back the indicator function, right? Take the conjugate twice, and I get that back. Okay, so now this is actually quite close to what we're asking. What's another way of expressing the norm function? It's the max of, I'll say, z in what set? With dual norm less than or equal to 1 of x transpose z. Right, this is because again, I'm using the fact that the dual of the dual norm is the same as the original norm. Okay, this is a way of expressing this norm. So it fits this form. If I take its conjugate, I should get that it's the indicator that a point is in this set, having dual norm less than or equal to 1. So we just proved this, this fact here without having to check anything else. We don't have to go through all that math on the slide. Okay, because this direction was trivial. Look, the fact that the conjugate of the indicator function is the support function, there's like no argument there. And now let's just rely on the fact that taking two conjugates gives us back the original function. We don't have to prove the kind of hard reverse direction. Okay, so before we leave, I want to go through a concrete example involving conjugates and relating them to duals so that we don't leave thinking, kind of, gosh, conjugates are this mathematical construct that seem a bit foreign. So here's how you might use them, for example. I'm going to drive the lasso dual. So this example is going to illustrate a few points. So how do I derive the dual of this? It's unconstrained. Its dual function is, so remember L, the Lagrangian is a function of x, and I have no constraints, so it's only a function of x. So it's just this same thing. And then the dual function is a function of nothing, right? I have no dual variables. So I'll write of the empty set is the minimum over all x of the Lagrangian, and that's just f star, right? If this was f, it's just the optimal point of our problem. So it looks like the dual is like a vacuous construct here. The dual is just a constant. It's equal to the optimal value of our criterion. Of course, it's a lower bound on the optimal value of our criterion. It's equal to it. So this is a case in which you might look at this and think, okay, the dual is useless. But actually, this is where some of the tricks come into play. I can introduce an equality constraint that looks totally stupid. Right? I wouldn't do this for any other reason than getting the dual. I'll just write subject to z equals x beta. All right, it's still the same problem, right? I haven't done anything different. I just have two variables, beta and z. And now what's its Lagrangian? Well, it's a function of x and z. Those are my variables. But also a dual variable, and I'll call it u, that corresponds to this equality constraint. So it's y minus z squared plus lambda L1 norm of beta plus u transpose z minus x beta. Okay, so to get the dual function, I want to minimize this over x and z. Minimize out my primal variables, and it'll be a dual in terms of u. So we can do that explicitly here. Let's just consider the minimum over z. So let's collect the terms that involve z and x separately. So I have y minus z squared plus u transpose z. And I have plus, I'll write this like this, lambda times the L norm of beta minus x transpose u over lambda, this whole thing transpose beta. Okay, I just did that in a form that for a reason that you'll see in a second, but it's the same thing, right? These lambdas cancel, and I get x transpose u, that whole thing transpose beta. That's just this, u transpose x beta. And that first term was just lambda times the L norm of beta. So I want to minimize over z and beta. I can do them separately. Oops, I had an x here. That was probably confusing you guys. Beta is my variable. So this one, I'm just going to tell you what it is since we're running out of time. But you can easily check this by taking the derivative, setting it equal to 0, plugging in for the optimal value, or also using conjugates. But this is equal to 1/2 y squared minus 1/2 y minus u squared. So when I minimize this over z, so min over z, I get this. It's a function of u alone. How about this part? I need to minimize this over beta. Well, what does this look like that we just learned? So hence, let's just group this whole thing together. It's the conjugate of the L1 norm evaluated at this point, right, times lambda. So this thing is just lambda times the conjugate of the L1 norm evaluated at this point. So it's lambda times the indicator of being in the set. What's the set I'm supposed to write here? Set of all, we can just call it, V such that, right, V infinity norm is less than or equal to 1. That's the dual of the L1 norm. So it's the indicator of the dual norm unit ball of the point. So X transpose U over lambda. Okay, so what is this? This is either equal to, it's infinity when this is not having, when this quantity has L1 norm bigger than 1, or it's 0 when it does. So this lambda in front doesn't do anything. So in terms of the role it plays in the minimization, now I'm going to write G of U. It's the minimum over beta and Z of L of beta ZU. It's equal to, so this can be equal to 1/2 y squared minus 1/2 y minus u squared when I have X transpose U having infinity norm less than or equal to lambda. That's another way of just saying X transpose U over lambda is infinity norm less than or equal to 1. And otherwise, it's infinite. Oh, I think nobody corrected me here, but this is actually the negative conjugate, right? The way we defined it. It's a point transpose my variable minus my function. So it's minus the indicator. And actually, it's negative infinity. Okay, so what's the dual problem? It's to maximize G. So the dual problem is as follows. It's just maximize G over all variables U, 1/2 y squared minus 1/2 my minus u squared, subject to X transpose U being less than or equal to lambda. This just translates into a constraint. Because when it's not true, the dual function is minus infinity. So when we're maximizing, we translate it into a constraint. Okay, so that's the lasso dual, this problem right here. A few subtleties. So the trick, okay, tricks and subtleties. Trick was to add this constraint, right? This Z equals X beta. So you'll often do that a lot with unconstrained problems. When it's unconstrained, you want to drive a dual, add a trivial equality constraint, and you'll be able to drive a dual. Where do the conjugates come into play? Well, you saw they came into play right here, right? To minimize this part of the Lagrangian, I used a conjugate argument, and that'll be generally true. That's what Sohail brought up, and the next slide that we won't cover today, but maybe cover on Tuesday, we'll just say that in a little more generality. And then what's the subtlety? The subtlety is as follows. So this is the dual problem, right? It's max 1/2 y squared minus 1/2 y minus u squared. That dual is equivalent to minimize y minus u squared subject to X transpose U in an infinity norm being less than or equal to lambda. I threw out the constant, and then it was a maximize a negative thing, so I changed it into minimize. This is an equivalent problem. So often when people write down duals, they'll call this the dual. But I'll put it in quotation marks. This is not really the dual. It's equivalent to the dual. So why am I making such a big deal out of this? It seems like it shouldn't really matter. Well, it's because of the fact that the optimal criterion value here is different than it is here. Right? So we know that at optimality, we have f of, say, let's write the solutions as hats here. f of beta hat is equal to g of u hat, where this is g. This guy is g of u. Let's call the criterion function here g tilde. That's not the same as g tilde of u hat. Right, I dropped the constant, I changed the sign. So even though I might want to solve this problem in practice, because the constant doesn't matter, and I like to think about minimization problems, if I ever check the duality gap and I plug in this for g of u hat, it's going to be wrong. Right, so it'll be wrong algorithmically. I won't even see that at the solution that they're the same. They'll have the wrong sign in this case. So you have to be careful, because a lot of times you'll have a dual problem, and then you'll reduce it to something easier, to an equivalent problem. But if you ever use the duality gap, you have to remember what the original criterion value was. Or if you want to say that they're actually the same in optimality, it's just the original criterion values. What's another subtlety? Well, another subtlety, and the last thing we'll end on, is that so I wrote this problem like this, where I said z is equal to x beta. What happens if I just said, I wrote down this equality constraint problem, which is also the same. Y minus xz squared plus lambda times L1 lambda beta, subject to z equals beta. So that's the same as the lasso problem too. Instead of substituting z for this whole thing, I just substitute it for the beta in there. But actually I claim, and you should go through and check this, that you get a different dual than the first one I wrote down if you take the dual of this problem. Okay, we know that it has to be equivalent in the sense that at its optimum, it's going to give us the same as this primal problem from our general kind of knowledge of duality. But it's going to be a different problem. And actually, this one's harder to solve. So if you go and you derive this dual, it'll involve a matrix inverse, like an inverse of x or x transpose x or something, I don't remember. But it'll be harder to solve. So it matters what I substituted. It's another subtlety. So you should, if you're ever doing this on a problem that you don't have a feel for yet, think about what are the ways to derive the dual. There could be more than one if it's an unconstrained problem. Some of them could give you harder problems than others. Okay, we'll end on that, and have a good weekend. We'll see you on Tuesday.
I have a quick question. Who doesn't know reproducing kernel Hilbert spaces? Reproducing kernel Hilbert space. Who knows? Who doesn't? Doesn't? Okay.
I assume anybody who doesn't raise their hand who doesn't.
If they knew, then one problem could be to estimate Kullback-Leibler divergence. So you want to estimate integral P over Q without estimating P and Q, and you can use Fenchel conjugate functions to do that. But you have to use.
Do they have to know RKHS for that?
I might rephrase it such a way that